Hi everyone and welcome to this new series of practice problems about electromechanical energy conversion. And in this series we will be dealing with different topics like magnetic circuits, DC machines, mainly DC motors, AC machines, we'll talk about synchronous generators and induction motors, and also we'll talk about transformers. So we will start by handling problems dealing with magnetic circuit. So in this question here, we have a magnetic circuit. What is a magnetic circuit? It's a circuit that has basically two main things, a coil, and the coil will carry a current, and that current will be responsible to produce a flux. And then you have the magnetic material where the flux go through, and this magnetic material might have air gap between the different branches. Okay, so that's basically a magnetic circuit. Now, when we deal with this problem, always we want to find the equivalent electric circuit. Why? Because we are more familiar with electric circuit than magnetic circuit, so it's easier for us to visualize. So always we'll try to draw the equivalent circuit. Now, in a circuit, we have the voltage or the EMF, we have the current I, and we have the resistance. So in the magnetic circuit, we have the MMF, which is equivalent to the EMF, and we will have the reluctance, and we have the, which is equivalent to the resistance, and we have the flux, which is equivalent to the current. So when you look to such a magnetic circuit here, the first and the most important task before even reading the question is trying to find what is the equivalent electric circuit. So in this, we have one source of magnetic field or one source of MMF. So this will be your MMF. Now this will be producing the flux. How? Now when the current goes into the coil, so your four fingers will be in the direction of the current. This will be the direction of the flux. So you'll have the flux going in this direction. Now as you can see here, the flux will be going all the way until it come back. So we have only one loop in the magnetic circuit. So we will have only one loop in the electrical equivalent circuit. And now we have two materials. We have the magnetic circuit and we have the air gap. So here we will have reluctance of the core material and reluctance of the air gap. So this is my equivalent circuit. Now let's see what do we want to find in this. We are given usually the dimension, so we are giving AC, which is the cross-sectional area of the core material. This is your A. This cross-sectional area is your A given to you. And we are giving that the mean core length. So it's giving you the mean length of the core, which is this dotted line that I am drawing. This is called the mean dotted line, or sorry, the mean core length. We have the air gap length, G, is equal to 2.3 times 10 to minus 3. We know the number of turns is 83. So your N is equal to 83 turns. And we will know the current, or we know the current is 1.5 amps. So the first part in this question, we will assume the permeability, which is mu, which is equal to mu 0 times mu r is equal to infinity. So we have a perfect magnetic material. Under this condition, we want to find the reluctance of the core and the reluctance of the air gap. The reluctance formula, generally speaking, is equal to L, which is the mean length, divided by mu, permeability, times the cross-sectional area. That is the general formula for the reluctance. So from this, you can find the reluctance of the core equal to L. What is L? It's 0.6. And you have to keep track of the units. So keep all the length as meter, all cross-sectional area as meter square. So this is already given to in meters. We keep it as it is. Divided by mu is infinity times A, which is equal to 1.8 times 10 to minus 3 meters square, and obviously this is equal to 0. When you have a material with an infinite permeability, it means it has no reluctance. Same like when I said the material has an infinite conductivity, it will have 0 resistance. Same thing. Now, the reluctance for the gap is equal to, same thing, L of the gap is given as 2.3 times 10 to minus 3 divided by, now, mu for the air gap, mu r is equal to 1. So we have only mu 0, which is a constant, which is 4 pi times 10 to minus 7. This is your mu 0 times the cross-sectional area, which is the same cross-sectional area we have, which is equal to 1.8 times 10 to the minus 3. So we have everything in place. We can find the value, which is 1.017 times 10 to power 6, and the unit is ampere turn per Weber. So this is your reluctance of the air gap. Now, for the current I equal to 1.5 amp, find the total flux. Okay. So what I help us to find, it help us to find the MMF, because the MMF is equal to N times I. So I know N and I know I, so I can find the MMF. Perfect. Now we apply just KVL. So this is the flux, so apply KVL. So your flux times RC plus reluctance of G is equal to NI. So from this, you can find your flux. Your flux is equal to NI. N is the number of turns, 83, times I, given to us also as 1.5, divided by the summation of the two reluctances, but this is equal to 0. So this is equal to 1.017 times 10 to power 6. And you will find that the flux is equal to 1.224 times 10 to minus 4 Weber. This is your flux. So we are done with the flux. You want to find the flux linkage, very straightforward. The flux linkage is just the multiplication of the number of turns times the flux. So we can easily find that. N is 83 times the flux, which is 1.224 times 10 to minus 4. And this will give me 101.6 times 10 to minus 4 Weber. Okay. Now we are done with ABC. In part D, it says repeat A to C, but now we'll assume a finite core permeability, which is equal to 2,500 times mu 0. That's all. So all you need to do is just repeat just calculate RC. That is the only difference. So your RC now will not be 0, will equal to L C divided by mu 0 mu r times AC. Now AC is equal to 0.6 meter. We already know that. And this is equal to 2,500 times mu 0, which is 4 pi times 10 to minus 7. So this is nothing but mu r times mu 0 times AC, which is equal to 1.8 times 10 to minus 3. We found the reluctance is equal to 0.1062 times 10 to the power 6 ampere turn per Weber. Now, what will be the reluctance of the air gap? It's the same thing. Nothing changed here. The only thing that changed is the reluctance of the core material. So now we want to find the flux. Finding the flux, again, it's Ni divided by the reluctance of the core plus the reluctance of the air gap. Now, the only difference here, we have a reluctance. So we expect the flux to be reduced, and indeed it does, and it's equal to 1.108 times 10 to minus 4 Weber. And for the flux linkage is nothing but N times phi, which is equal to 83 times 1.108 times 10 to minus 4, which is equal to around 92 times 10 to minus 4 Weber. So this is a very, very fundamental basic question that talks about the impact of if we assume mu r is infinity and how to include the air gap in a simple magnetic circuit.